Welcome to LoRaWAN Fundamentals. My name is Johan Stokking. I am CTO and co-founder of the Things Industries and tech lead of the Things Network. I'm also chair of the security work group of the LoRa Alliance. And in this video, I'm going to present you everything that you need to know about LoRaWAN. So I'm going to talk about LoRa, the modulation, LoRaWAN, the protocol, some security aspects that are important to know. Also, something about end devices and gateways, and finally, how to get started. But first, why is LoRaWAN so awesome? So there are 10 reasons that make LoRaWAN unique. You find these things also in other low-power, wide-area networking technologies, but this set of features, the combination, is really powerful in LoRaWAN. So first, it's ultra-low power. It's long range, it has deep indoor penetration, it makes use of the license-free spectrum, so you don't need to obtain a license to deploy a LoRaWAN network. It supports geolocation, and that means that the network can determine the location of your devices. LoRaWAN is also unique in the ability to deploy both public and private networks with this very same devices and the same gateways and the same software. Also, it has end-to-end security built in right into the LoRaWAN protocol. It supports firmware updates over the air. There's a certification program. And finally, there's a very large ecosystem of device makers, gateway makers, network service providers, as well as application developers. Some of the use cases are natural disaster prevention, agriculture, also lots of industrial use cases like monitoring of industrial sites over long range, but also controlling things, controlling valves, for example. LoRaWAN is also really powerful in smart city use cases, monitoring buildings, and also obviously supply chain. And smart metering. There are many different use cases in LoRaWAN, and that also makes LoRaWAN really powerful. Is that it's you can use it in many different verticals and areas. There are many network operators, and it's really a global technology. So you can use LoRaWAN all over the world, everywhere where there is there are regulations with a license-free spectrum, and it's basically everywhere. What does a LoRaWAN network architecture typically look like? So this is the topology. On the left, you see the end devices. They are connected to a gateway. Actually, there's not really a connection between an end device and a gateway, but the gateway is basically listening for messages that end devices are sending, and the gateway is transparent. It passes the message, it forwards the message to a network server. And the network server identifies the end device and does some security stuff, some network management stuff that I'm gonna present later. And then you have on the right side the application layer. So that's typically what you as a solutions developer use to get your data, to manage devices, to check the status, to send messages back. And that's typically just internet APIs that you're used to. So what's the difference between LoRa and LoRaWAN? So LoRa is the physical layer, and in here in this slide, it's the layer below. So you have different regions, different bands. So in Europe, for example, in the US, in Asia, there are different frequencies that you can use. And then there's a LoRa modulation. And LoRa modulation is really about transmitting data over the air and doing that in a very efficient way over long range. And I'm going to show you the physics also. That's very interesting. So that's LoRa. That's really just getting data through the air. Then in yellow, that is what LoRaWAN does. That is a MAC layer, media access control, and the MAC layer is doing all the security features in LoRaWAN, activating devices on a network, frame counting, acknowledging messages, synchronizing the windows that your application can send data to the end devices and things like that. And then on top in blue is any IoT application, basically. So first, LoRa. So LoRa is really complementary to existing IoT communication technologies. But LoRa is unique in that it's long range, but obviously at the cost of bandwidth. So it's designed for IoT use cases which require only very little bandwidth, very small messages. But that also makes it really useful for devices that are usually asleep. There's very little overhead to have the device on the network. So it can basically be in deep sleep most of the time. And when a message needs to be sent, it just wakes up, sends the message, and goes back to sleep. And that really makes it complementary to other IoT technologies. It's not a replacement. In fact, we also see end devices that both have a Wi-Fi transceiver as well as LoRa, and only enable Wi-Fi if they need a high throughput. LoRa can be used in a license-free spectrum, and the thing is that the license-free spectrum is not globally harmonized. It's not like a Wi-Fi 2.4 and 5 gigahertz, where Wi-Fi and Bluetooth make use of, which is globally harmonized. That is unfortunately not the case with sub-gigahertz frequencies. And that means that in different regions, you have to use different frequencies. And to make that easy, LoRaWAN has a regional parameters. That's a specification. For each region where LoRaWAN is supported, and that's in 150 countries, you can find all the frequencies for that region. And your end device, as well as a network server, make sure that this all works and it's all part of the regulation. So usually you don't really have to think about this, but it's important in case you want to design and ship devices to different regions, because then you need to have two versions for the US and the European market, for example. So then the modulation. LoRa uses a chirp spread spectrum modulation, and the main characteristic of that is that there is a bandwidth in which the communication symbols are modulated. And that means that there is a center frequency, and around that center frequency there are symbols modulated, and you see that here on the right in a spectrogram. So you see those symbols, and the bandwidth is quite high. It's typically 125 kilohertz. And that makes it different from, for example, a narrowband waveform, which chooses a center frequency and then uses that single frequency to send data. That makes it, the spread waveform makes it robust to interference, because only if there would be another signal that would make use of the same bandwidth at the same time, exactly following the same pattern of these symbols, only then you would see interference. So LoRa is super robust to interference. Actually, the chirp spread spectrum modulation is also used by whales and dolphins and bats. So they also use it in nature to communicate with each other, but also to use to find their prey. And this also works over very long distance. So that's where the chirp spread spectrum comes from. So looking a bit into the modulation itself, when an end device sends a message, it sends 8 of those chirps. So you see them here on the left. Then there are 2 down chirps, so that's the other way around. And then there are again more up chirps with the data. And this is an indication for the receiver that there is data coming. So it's like a small chirp, it's like an announcement saying, hey, there's data coming, I want to send you something. On the demodulation side, so on the receiver side, the inverse happens. So there's de-chirping, and then there is a spectral analysis to figure out what the symbols were that were transmitted by the sender. And so I'm saying sender and receiver, not necessarily end device and gateway or network. Because the beauty of LoRaWAN is that this modulation and the demodulation is so simple that it can also be carried out by the end device. So by your very cheap, low power end device, it uses the very same technology for both directions of messaging. And that also makes LoRa unique. So there are LoRa devices and LoRa gateways. The difference between the end device and a gateway is that a gateway can listen on multiple frequencies at the same time. So they have multi-channel, and that's why it's called a concentrator. And an end device can only do one. But the modulation from device to gateway and from gateway to end device, that is just LoRa. We call the transport from end device to gateway, we call that uplink. And from gateway to end device, that is downlink. So that's important to remember. Then in LoRa, there is another important term, and that is the spreading factor. And a spreading factor indicates the number of data bits per second, the symbols that are modulated per time unit. So the higher the spreading factor, basically the slower the communication is. And you see that here also in this image. And increasing the spreading factor increases the time that it takes to send a message. And that obviously needs more power on the end device to send the message. A lower spreading factor has shorter range. It has less time on air, so it takes less time to send the message. And that's obviously better for the device's battery. And that also means that the data is transported faster, so the data rate is higher. And this is a choice. This is a choice that you make on the end device and on the gateway, what the spreading factor is that you use for communication. And this is always a trade-off. There is no single spreading factor that is best for your use case. And that is why LoRaWAN has a mechanism called adaptive data rate. Adaptive data rate is choosing the best spreading factor in a particular scenario. So if the end device is close to a gateway, the end device can use a higher data rate or a lower spreading factor to communicate. And if the device is further away, then you would typically go for a higher spreading factor and a lower data rate to ensure that the data is received by the receiving end. Adaptive data rate is an algorithm that can measure the signal-to-noise ratio. And based on the signal-to-noise ratio or the link quality, the network can instruct an end device to change the data rate, for example, to increase it. And that is really powerful in LoRaWAN, to automatically, dynamically adjust the data rate and thus optimize battery life and link quality. LoRa in the licensed spectrum, in the unlicensed spectrum, also has something that you need to consider is the duty cycle and the time on air. And that is that differs from region to region. So for example, in the European Union, there is a duty cycle, and a duty cycle is expressed in a percentage of time that your end device can transmit. And the rest of the time, it has to be silent. In the US, there is no such limit on the duty cycle, but there is one on the dwell time. And that is the time that it takes to send a message. There are differences in the subbands and everything. And again, this is all specified in the regional parameters. And your end device tag and your network already contains these tables and takes care of this. But it's important to note when you're deploying use cases. This also is the main reason why you cannot have voice calls over LoRa, for example, because then you need continuous transmission, and that is not possible. Not only for battery life, but also because of the duty cycle. So an example is, let's say you have a band, the first band, band 1, which has a limitation of, or a duty cycle of 20%, and in band 2 there is a duty cycle of 40%. There are 2 channels in band 2, so in total there are 3 frequencies, and if on each of these frequencies the duty cycle would be 20%, then that means that in total the device can use frequency hopping, so it can choose a different frequency, and has a time on air of 60%. So that's an example. And end devices, they use this frequency hopping, not only because it's mandatory, but also to optimize the channel utilization. And again, this is typically only applicable to European deployments of LoRaWAN. In the US, there is no duty cycle, and also in many other regions in Asia and in Australia, but there is dwell time, or there are other limitations. Apart from the legal framework and the legal limitations that you have in different regions, you can also have limitations set by the network operators. And this is common for public operated networks that are provided by a traditional carrier. You can have prepaid plans for the number of messages that your device can send per month or per day, for example. And sometimes for network optimization, there could be another policy. So for example, in the Things network, which is a free community network, LoRaWAN network, for optimization and for overall network capacity, we also have guidelines. They don't apply to private networks. If you deploy a private network with your gateways and your network server, you only have to take care of the regulations in your area. But don't waste any airtime. It's not only for the network capacity, but it really is also the battery life of your end device that is influenced by the spreading factor, the data rate that you use. So we have a calculator. If you go to thethingsnetwork.org/airtime-calculator, you can find there a very small, simple calculator where you can enter the size of the payload that you want to send and the spreading factor, and then it shows you how much milliseconds it takes to send a message. And if you need 2 or 3 seconds to send a message, that obviously draws more battery power than a higher data rate or a lower spreading factor. So then range, that's one of the key benefits of LoRa. So there is a mathematical model to calculate the free space path loss. So that's the distance that your transmission can travel, that it can still be received by the endpoint, by a gateway, or the other way around, by the end device. So the free space path loss is this formula, and it takes into account the distance between the transceiver and the receiver end, as well as the frequency. And this is also why a lower frequency sub-gigahertz communication is longer range than a higher frequency. So only because of the frequency, the range is longer because it's sub-gigahertz as compared to Wi-Fi or Bluetooth, which operate typically in 2.4 and 5 gigahertz. Now here you have the overview. On the left, you see the transmission power. That's in dBm. On the right side, you see the RX power. So that's on the receiver side. Now the RX power is the transmission power, so that's what the transmitter used to transmit the message, plus the antenna gain for transmitting the message. There is some connector loss, so that's negative on the transmitter side. And then on the receiver end, you have also an antenna gain and some antenna loss. And then the goal is obviously that the resulting RX power is higher than the receiver sensitivity. If it's below the receiver sensitivity, then your message gets lost in space. So this is what you don't want. So your receiver sensitivity needs to be sufficiently low, or your range should be sufficiently short to receive the message. So that's what you want, basically. And you can calculate all of this. So the receiver sensitivity is also a formula. It takes into account the thermal noise of the bandwidth, in this case, room temperature. The bandwidth that's used. So here, the spreading the spread spectrum aspect of LoRa is handy because that's a high bandwidth. Then there is the signal to noise limit, and this is a number that depends on the data rate. So here is the factor of the spreading factor that influences the range directly. Then there is a noise figure, so that's a hardware characteristic, and then you have a link budget. And the link budget is what determines range, and I'll get to that in a bit. So this is the overall formula. You don't have to know this formula on top of your head to pass the LoRaWAN fundamentals certification, but all these factors are all relating to the range and also why. So here's an example. With 125 kilohertz bandwidth, so that's the typical bandwidth used in LoRa communications, a spreading factor of 12, that's the highest spreading factor or the lowest data rate, which is best for the longest range. There is a signal-to-noise ratio limit of 20 dB, minus 20 dB, a noise figure, 6 dBm, that's a characteristic of the end device. And then when the receiver uses 14 dBm, you can calculate that the receiver sensitivity is minus 137 dBm. And if you measure the difference between plus 14 dB of the transmit power with the RX sensitivity of minus 137, you get a link budget of 151 dBm. So that is what you see here. You have the transmit power on the top left, that's 14. You have the receiver sensitivity of minus 137, and that gives you a link budget of 151. So what does that mean? What does 151 mean? So here you see a comparison with other wireless technologies. So in Wi-Fi, for example, the transmit power is higher, so that draws more battery. The receiver sensitivity is also higher, and that means that your link budget is much smaller. It's 95.5. LoRa is 151, and you can do the same calculation for narrowband IoT, which is a cellular IoT technology, which has a similar link budget. But you see here also that LoRa reaches a similar link budget, 151, with much less transmit power. And this is a logarithmic scale. It's in fact 8 times more power for narrowband IoT, 8 times more power to get the same link budget than with LoRa. And that also makes LoRa, just from a physics standpoint, much better for battery life. So that's the theory. What does that mean in practice? Well, thanks to the Things Network community, there have been a lot of experiments with finding what is the practical limit, what is the real range that you can get with LoRa. So there have been community members that set up senders and receivers on mountains in the Alps, for example, and they reach hundreds of kilometers of range on Earth. So that's already quite promising. So the theoretical maximum is 850 kilometers with the free space path loss algorithm that I showed before. And during the Things virtual conference in early 2020, there was another experiment with a helium balloon. And with a small transceiver that sends a message with normal spectrum regulations for Europe. So that's 14 dBm or 25 milliwatts of power. It sent a message from all the way from a weather balloon. I think it was like 36 kilometers of altitude, and it reached the gateway in Czech Republic, and that's 832 kilometers. So that it's real. And then the question is, why can't you cover all of Europe or all of the US or all of Australia with a single gateway? And that's obviously because free space is only in space. And on Earth, we have factors like the structural attenuation, so that's the material, buildings, for example, trees, things like that. There's reflection and diffraction. So there are buildings with a lot of glass that reflect the RF signal. And also there is a Fresnel zone. So even if you have a line of sight, still there has to be a lot of line of sight basically around it to communicate well. So all these factors negatively influence the range. So interference and multipath, there have been quite some scientific research on this topic, and the experimental results so far are that LoRa has a very high immunity to these phenomena, especially in low data rates, and so the higher spreading factors. And what's nice about the adaptive data rate is that this can dynamically be configured, and also that since it's unlicensed spectrum, anyone can set up gateways, and that also means that if you need better coverage, if you need to have gateways closer to an end device, you basically buy a gateway and install it there because you don't depend on a public operator to do so. Finally, another physics aspect that's important to note, and that LoRa performs really well in this aspect, is the Doppler effect, and that's the when a device would be moving really fast from away from a gateway or towards a gateway. So it's the same effect as if you hear a police car passing by and you hear that the serene changes in sound. That's the same with it's changing the frequency. And LoRa has proven to be super robust also against this effect. And that means that you can also install LoRa devices on moving objects like cars and trains and even airplanes sometimes. So what are the considerations? It's always better to install gateways outdoors and on higher altitudes. And there's also also quite some research on this. So it's really hard to say beforehand what the range of a particular gateway in a particular setup will be, because it depends on so many different things. And there are also different gateways, and I'll get to that in the end. So the range depends on indoor or outdoor placement, as well as the elevation of the gateway, and also obviously the elevation of the end device. So summarizing on LoRa, it's long range, it's very low power consumption. Because of all sorts of mechanisms, you can have a very high network capacity. Its robustness is robust to many different things like interference, multipath, fading, Doppler effect, and that makes it a really good choice for IoT solutions. So then LoRaWAN. So what is LoRaWAN? LoRaWAN is a protocol. It's a communications protocol that can be used typically on top of LoRa. And LoRaWAN has different regions. So there is a regional parameters document that I already mentioned a few times, and that describes all the regions where you can use LoRaWAN and all the frequencies to use and what are the limitations and things like that. And you can often find these already implemented in libraries that you can use for end devices and on the network server. But it's just good to know. So there are frequency plans, and for example, in the US, the band is called US 915. It goes roughly from 902 megahertz to 928 megahertz, and the US 915 is a band where there is a fixed number of channels. It's 64 channels for uplink that are 125 kilohertz in bandwidth, and then there are 8 channels that are high-speed channels, 500 kilohertz bandwidth. And then for downlink, so communication back to the end device, there's another 8 channels defined. So that's just how the regional parameters define a region, just as an example. what's really important in LoRaWAN is the device classes, and there are 3 of them. You have Class A devices, and Class A is implemented by all LoRaWAN devices. And Class A is that the end device can initiate a transmission. So the end device can just send a message at any time. This is typically used by devices that are measuring things like sensor nodes, but it can also be devices that on a regular interval they send a heartbeat saying, hey, I'm still here, this is my battery level, and I can, all my sensors are working, for example. Class B is beaconing. That's basically the best way to remember it. And the beacon is sent by the network on a fixed interval by gateways, and the end device can pick up this beacon and wake up to receive a downlink message. So Class B devices, they are in deep sleep, but they wake up on a time interval. So for example, every half a minute or every 2 minutes roughly, and they listen for traffic from the network. And this is not as low power as Class A communication, but it allows the network to send a message to the end device, even though the latency is sometimes tens of seconds or at most a few minutes. And then finally Class C, which stands for, or is easy to remember, is continuous downlink, means that the end device is continuously listening for downlink messages, and this allows the network to send a message to the end device at any time. Typically, this is a temporary mode for an end device, so it can be temporarily listening for downlink messages. It can also be that it is an end device that is connected to a power source, for example, street lights, so you can turn them on at any time, and they already have a power source because that's the light, so to say. So on the right you see the differences, Class A, B, C, and the main difference is the battery lifetime, with the trade-off being the communications delay. So device classes, this is how it works. There are so-called receive windows. So the end device can send a message. That's what you see here in green. Then there is a RX1 window. So that's the first receive window that's always opened when a device sends a message. It follows by a second receive window, which is exactly 1 second after the first window. So those are the opportunities that the network always has when an end device sends a message. But with Class B, this receive window comes back on an interval, so that allows the network to send a message every, like I said, every tens of seconds, every half a minute, minute, or 2 minutes, for example. And in Class C, this window stays open all the time. And when there is a blue window or a yellow window here, the network can send a message to the end device. So some of the limitations. The payload size is oftentimes very limited. So depending on the data rate, in a very low data rate, so a high spreading factor, the limit is typically 51 bytes. If you use a higher data rate, then the limit goes up to 241 bytes. It's highly recommended to use a very smart and simple binary encoding mechanism for payload. So don't send any text, don't send any JSON, certainly not send any XML messages, but really be mindful about the bits and the bytes that your end device is sending. Typically, you would decode those bytes on the server and transform it into a JSON object that makes sense to the application layer. Another limitation is the data rates. So the transmission is quite slow. It's up to 5.5 kilobits per second. There are different rules in different regions. That can also be a limiting factor when designing LoRaWAN devices. So in the EU, there's a duty cycle. In the US, there are dwell time restrictions. And it also means that the certification program is different for these regions. Finally, the communication is asynchronous. So your gateway is also a device that has to comply with the spectrum regulations. So a gateway also has a duty cycle. And that means that a gateway in the EU, for example, is also limited in how many messages it can send. And that means that most of the time, the 90% of the traffic, if not more, is uplink, is from the end device towards the network, whereas downlink is typically limited. Then a few things on LoRaWAN security. First, the physical layer, LoRa, does not provide any security. So even though you can use LoRa chips and LoRa concentrators to communicate over long range, you get all the benefits, it doesn't provide any security mechanism. It only contains a checksum, a CRC, if there haven't been any symbols flipped, any bits flipped. But any other mechanisms are not provided by the physical layer. For that, you really need LoRaWAN. And LoRaWAN provides security on the 3 pillars of security. So the authenticity, the integrity, and the confidentiality. So authenticity means that you know with which device you are communicating. It's authenticated. Integrity means that the data that is being sent and received is not tampered with. So you know for sure who sent the message, but also that the message hasn't changed by an intermediate party. And finally, the confidentiality means that you can encrypt the data, so that on the application layer, for example, the data is encrypted and that the network cannot see what the payload is. So how does that work? LoRaWAN provides security on 2 different layers. First, the network layer, and that is security is provided by the network session key. And second is the application layer. And the security there is provided by the application session key. So the network S key, session key, and the app S key, the application session key. The network session key is used for integrity and authenticity, whereas the application session key is used for confidentiality. These are AES 128-bit keys, and that is in industrial standard for securing communications. And at the same time, it's still relatively cheap for end devices to implement AES 128-bit. So then there is a LoRaWAN session, and a network session is a session actually comes in 2 sessions that the end device has, one with the network and one with the application. So that also is the network session key and the application session key. There are in fact 2 sessions. The network session contains a device address that's a 4-byte address that's issued by the network server. There is a network session key, and there are frame counters, and there is some MAC state, so the media access control state. So the frequencies that are being used, the delays, the data rates, things like that, everything that the LoRaWAN network server manages. The application session is secured by the application session key, also has frame counters. And during a session, the session keys don't change, and the frame counters are incremented, and the state can be changed. But the device can reset the session. And that's the difference between the 2 activation modes. So a session can be established dynamically by joining a network, and that's called over-the-air activation, or OTAA. And this involves a join procedure. So the device, when it is not on a network yet, it sends a join request, basically requesting to join on a network. And the network server, any network server can respond to that device to allow the device to join that network. And that requires the network to perform some cryptographic operations, and that the device is also allowed to join that network. And every time the device joins a network, there is a new set of security keys generated. So there's a new network session key and a new application session key. The alternative is a hard-coded session. So that's called ABP, Activation by Personalization. And then there is no join procedure. In fact, the end device gets hard-coded, pre-programmed, a device address, and the session keys. And this is typically more efficient because you don't need a join procedure, but obviously it's not as secure because you cannot really change networks throughout the lifetime of the end device. So which one is safer? It's highly recommended to use over-the-air activation because there is a new session every time the device joins. Instead of ABP, it's always the same session. Over-the-air activation also allows rekeying. You can even, with a newer LoRaWAN version, you can even instruct end devices to join again. Whereas if you have an ABP device, the session keys, they are stored somewhere in that end device and they will never change. With over-the-air activation, you can also join any LoRaWAN network, and you can even change from network to network. Whereas in the case of ABP, you can also do that, but then you need to copy all these keys to different networks, and you cannot require other networks to forget those session keys. So it's a trade-off between security and resource constraints, but typically prefer over-the-air activation. Session keys. So I mentioned already the application session key and the network session key. Those are keys that are generated from a root key, in this case the app key. That's in LoRaWAN 1.0.x, generation of LoRaWAN. In LoRaWAN 1.1, there are keys per purpose, and there are two root keys. So there is still the app key, and the app key is used to generate the application session key with the sole purpose of encrypting and decrypting application payload. And then there is another root key, and that's a network key. And a network key is used to generate three different session keys that each have their own purpose. So it's integrity checks for a forwarding and a serving network. It's in case if a device is covered by another network and there is a traffic exchange between two networks, you can share the forwarding integrity key with that network. I won't go into all the details now, but that's integrity check. And then second is the encryption key, and the network session encryption key is used to encrypt instructions that are sent to the end device, for example, to change data rates or to change delays or to use a different frequency or things like that. So that's the key derivation for the different session keys. So LoRaWAN security, end-to-end security is provided by what you see here in red, the application session key. In light blue is the security contract between the end device and the network server, which is enabled by the network session key. But then a gateway is just any internet connected device. So it has an IP address, it has somewhere deployed, and you also want to have a secure connection with your gateway. But you can use any industry standard for that. So you can use TLS certificates to connect gateways, or API keys or things like that, or IP security, or you can make them part of a VPN, as long as they have a secure channel to communicate with the network server. And the same goes, obviously, from the network server to the application server. We typically use industry standards for that, TLS, API keys, TLS client certificates, things like that. A few things on privacy. So LoRaWAN is a protocol, and it uses a unlicensed spectrum. Anyone can set up a LoRa gateway, and if you do so, then you start receiving LoRaWAN traffic. So even though the payload is encrypted, there's a bunch of metadata that is public. And application developers, LoRaWAN developers, need to be mindful of what those fields are. So when a device joins the network, for example, it sends the join EOI, that's a pointer to the join server, which is a component that generates those session keys. It sends the depth UI, this unique identifier of the end device, and that just flies through the air. That's fine. And as soon as a device has a session established and it sends a message, there is a device address, there are frame counters, there are ports that are being used, and the length of the payload, the length of the frame. So that's all public. So there are some recommendations on how to make sure that eavesdroppers, even though they cannot read payload, they also cannot know what the payload could potentially mean, or which device it is, or who owns the device. That is important to keep in mind. So when you provision end devices, you need to program them with a join UI and an app UI, and you want to share the root key, so the app key and the network key, in a secure way. So if you are a device maker, you need to have a secure way to transport those root keys to somewhere on the network where the owner of the device can activate these devices with. So what you don't want to do is to send these root keys in an Excel file or by email or printed on paper to the customer, because then if the device gets get a change of ownership or throughout the distribution chain, it's really hard to make sure that only the rightful owner has ever seen those root keys. So in LoRaWAN, there is a mechanism using a specification that's called the LoRaWAN backend interfaces, and there is a concept of a join server, and that is a backend service that you can use to provision your root keys with, and the join server decides which network is allowed to activate the device on. And there could be a very simple claiming procedure. So you build your devices, you provision these root keys on a join server, and then you, when you sell the device, you also provide a proof of ownership so that the owner can claim the device and can go on the join server and say, hey, these are my devices. I want to use the Things network. I want to use my private network. I want to use a public operated network. And then the join server allows join requests from that network to activate your device. That's typically the recommended way. So that's a join server. It's a dedicated server for handling the sensitive part of the activation procedure on a LoRaWAN network. And so what the join server does, it authenticates a network server, an application server. It has a secure storage of root keys. And we typically see that join servers have a hardware secure module or an HSM to securely store these root keys. And the join server generates the session keys and gives them to the network server and the application server that are allowed to activate the device. So that's a recommended way of securing LoRaWAN. A few other security features in LoRaWAN are commands to check the link quality. And that can be useful for devices to know and to be sure that they are still on the network. And if they are not, for example, that they don't just keep on sending messages, but that they, for example, revert back to a join procedure to join a different network so that they don't get lost. There's also the ability to acknowledge messages. So to get a confirmation from the network that a message has been received. This could be uplink and downlink. So the adaptive data rate that I mentioned before, that is actually also a security feature because it reduces the packet loss. And having a high packet loss can actually lead to security vulnerabilities. LoRaWAN also comes with frame counters. Each message has its own frame counter within a session, and that avoids replay attacks. So even though the message can get picked up by an intermediate, it doesn't make sense to replay that message later because the network or the device will figure out that it has already received that message. And finally, there are numbers that can only be used once for the security of the join procedure when activating. So every join procedure is unique because of such nonce, a number used once. So for securing, a few tips. Don't share your root keys. Use a joint server. Use a unique root key for each end device, so don't use the same root key. Make sure also that the root key is not something that's generated from a serial number or anything, but it's really generated by a random number generator. Also make sure that you never reuse those nonces and frame counters, and that means that you need to have persistent memory in the end device, and you also need to have a network server that is obviously also respecting these security features. When choosing over-the-air activation versus activation by personalization, choose over-the-air activation unless you have a really good reason not to. And finally, make use of a trusted third-party joint server that doesn't lock you in to a certain ecosystem, but it allows you to activate the device on any LoRaWAN network, even your own. So then a few other best practices. There are a few optimizations that you can do. First, what is required is that your devices comply with the LoRaWAN specification. Also, best practice is to avoid sending many join requests. So every 10 seconds sending a join request and draining the battery, but use a backup mechanism. Also think about how often the end device sends a message. Do you really need to send the same temperature value every minute, or would you only send a change, or would you only send a heartbeat every hour, or concatenate different measurements in one larger message? So all those things are good to think about. It's always good to make sure that the message is as small as possible, because shorter messages have a shorter transmission time, which is always better for battery life, but it's also good for the overall network capacity. And finally, expect packet loss. It's not unavoidable. So make sure that your solution can still work, even if you lose maybe 10% of the messages. So allow for some redundancy. If the message is really important that it gets acknowledged by the network, use a confirmed message so that the network answers with the confirmation. But you can also use forward error correction. So you can also use data from the previous measurements and include that in recent messages. So maybe you send too much data, but at least you account for some packet loss. Also make sure that you don't synchronize all the devices so that they don't send a message all at the same time on top of the hour, for example, because then there could be congestion in the network and in the air. So use some random jitter, some random time to sleep, and also have a back-off mechanism. So if you cannot join the network, you can try again with a short interval, but maybe after some time, retry only every day or every 6 hours or so. Also, if your device is not moving, but if it's fixed on a certain location, always use adaptive data rate. So let the network figure out what is the best data rate for your end device, depending on the signal-to-noise ratio. Finally, I can't repeat it enough, prefer over-the-air activation. Use persistent memory in the end devices so that after a power cycle or even after replacing the battery, your device still can restore the LoRaWAN session, or if it cannot restore the session, at least it still has the nonces, the numbers that can only be used once, so that the join procedure is unique again. And also assume that there is a link loss only after some time, after missing, for example, 3 acknowledgements, and not after missing the first, because it can happen that one confirmation doesn't make the end device. Now, there is a LoRaWAN certification program that is provided by the LoRa Alliance. And the certification is something that you can get from different test houses around the world. So these are professional institutions that can test your end device and that can make sure that it complies with the LoRaWAN specification. And to make that easier, the LoRa Alliance also provides a certification test tool, the LCTT, that you can use yourself before submitting your device to a test house. So you can basically already know in advance if your device is going to pass the certification, which is a huge cost saver. Having a LoRaWAN certified end device also makes sure that it can be used on any LoRaWAN network, and that makes the addressable market for you as a device maker huge. Now, there are different LoRaWAN versions, and there has been quite some confusion about this recently. So there are certification programs for different LoRaWAN versions and for different regions. The first LoRaWAN version 1.0, the certification program is already withdrawn, and the same goes for the second version, 1.0.1. A very popular LoRaWAN version today is 1.0.2. It added lots of regions where you can use your device. In 1.0.3, which is essentially just a small addition to the previous version, which adds Class B and a few more regions. Then there is a huge a milestone, a big major version of LoRaWAN 1.1, which adds all these session keys. It adds supports for handover roaming, but it's not well adopted yet. It contains some really nice features, but the latest version is actually an iteration on 1.0.3, and it's 1.0.4. It has been released in 2020, and that is now the recommended LoRaWAN version to adopt. And I would recommend to wait for LoRaWAN 1.1.1, and until then, until that is widely supported and certified, and there are libraries available and things like that, and certification, the best version to use is 1.0.4. So LoRaWAN 1.0.4, it actually contains a lot of simplifications. There is a reference implementation for end devices, and that makes it very easy and quick. You can get started quickly. There is the certification test tool that's available for this version, so that also makes it really easy and also cheap to get your devices certified. And there are a few other specifications that are part of or that are compatible with LoRaWAN 1.0.4. For example, a QR code that can be used to claim your devices. So it already uses the terminology that's going to be adopted by future LoRaWAN versions. And there are a few security improvements, but they are more clarifications. So the size of the bit counter, for example, but also the requirement for persistent memory and things like that. So best LoRaWAN version to use today, 1.0.4. Devices. So LoRaWAN devices, why are they, for a solutions provider point of view, a very good choice? You have different device classes, so you can mix class A, B, and C. You can choose what your downlink capacity needs to be for your end devices. But in any case, they have very little power consumption. And you can choose the spreading factor, the data rates, the class, and things like that, and you can mix and match whatever you need. And that versatility and flexibility makes LoRaWAN a really good choice for solution providers. And there are many LoRaWAN devices. So you can go to the Things Network Marketplace. That's a huge catalog of LoRaWAN devices. And you can find LoRaWAN devices for just about everything. And the same goes for gateways. There are many different gateways, and there are all sorts of differences between them. So the regions, the software that runs on the gateway, the remote management, how many channels they have to listen on, but also the ruggedness and whether or not you can deploy it outdoors or not. If they have a cellular backhaul, or even if they have a backhaul to communicate with satellites. So these are all differences in gateways, but you can already purchase gateways for 50 euros and get started with a private network. So how to get started? You can start with the Things Network. That's our initiative. It's the largest LoRaWAN community. It's an open source and decentralized network that we operate. So it's a network of gateways, it's a network of things, but it's very much also a network of LoRaWAN professionals and people that are interested in LoRaWAN. It's the biggest LoRaWAN community, like I said, but it's also the biggest global LoRaWAN network. So we have tens of thousands of gateways connected. We have hundreds of thousands of devices that are active on the Things Network. We have deployments in just about every country. And also, maybe the most important thing is that it's really a people's network. So you can sign up, you can join a local community, you can go to meetups, also virtual meetups, and you can collaborate and contribute to the Things Network that way. And then when you get started and when you have your first devices and your first gateways and you start to see traction, you can scale your solution with the Things Industries. The Things Industries is the developer of the Things Stack. That's the network server implementation. It has an open source core, so you can find that on GitHub. It's one of the largest open source projects from the Netherlands, where we're from originally. And it allows you to build and manage your own LoRaWAN network. So you can get the open source stack, but you can also use a hosted and SLA-backed version that's offered by us, by the Things Industries. You can use your own hardware, your own devices, and you can get support, and you can even exchange traffic with the community network. So you get the best of both worlds. So that's LoRaWAN fundamentals. Now you should have enough knowledge and expertise to pass the Things certification, LoRaWAN fundamentals. Thank you very much for watching, and good luck.